So I want you to picture this. Just, imagine a sleek, totally silent 300 mile per hour levitating train.
Right. The ultimate dream.
Exactly. And it's running completely uninterrupted from New York City all the way to Los Angeles.
Oh, yeah.
It's like the ultimate American infrastructure fantasy, right?
Yeah.
The doors glide shut in Manhattan. You settle into this massive, spacious seat, and you are just hurtling seamlessly across the entire continent.
Yeah, until you come to that elegant, perfect halt in downtown LA.
Right. I mean, transit enthusiasts have been drawing this exact map, this sort of coast-to-coast ribbon of tomorrow, for decades now.
They really have. It's an incredibly beautiful vision.
It is. But here's the thing. It is also a guaranteed multi-trillion-dollar catastrophe.
Oh, absolutely.
Like, if we actually tried to build that beautiful map right now as our opening move, it would be a disaster so profound that it would basically kill the technology in this country for a century.
Yeah, the poster is glamorous. I mean, it looks fantastic on a presentation slide. Yeah. But the physical, the economic, and the political realities of actually executing that poster are entirely different.
Totally.
The fundamental physics of the technology completely reject the way we are used to, drawing lines on a map.
So today we are throwing away those romantic maps. We are doing a deep dive into excerpts from a strategic framework for national Maglev infrastructure.
Yeah, it's a fascinating document.
It really is. We are unpacking what is arguably the most radically pragmatic blueprint for actually building a U.S. Maglev system that has ever been put to paper.
We are definitely leaving the realm of science fiction here and stepping right into hard physics.
Exactly. We're looking at brutal, unforgiving economics. And surprisingly enough, we're looking at biology.
Biology, yeah. Specifically, brainless slime molds.
Which is just wild to me. But by the end of this, you will see why the future of American high-speed transit absolutely must start in the cornfields of Nebraska and not the congested, wealthy coasts.
It's a huge paradigm shift.
Okay, let's unpack this. Before we get to the slime molds, let's lay down the technical foundation. What are we actually dealing with when we say maglev?
Right.
Because I think a lot of people hear that word and they just assume it's like a really fast version of the Amtrak Acela down on the Northeast Corridor.
Ken, that is the very first misconception we have to dismantle. Maglev is not a train.
It's not.
Not in the traditional sense, no. It is a completely different technological species.
Okay.
When you look at legacy rail, I mean, even the incredible high-speed systems like the TGV in France or the Shinkansen in Japan, you are still looking at steel wheels physically rolling on steel rails.
Right, there's contact.
Exactly. There is mechanical contact.
Yeah.
And that means there is friction, there is vibration, and there is immense wear and tear on both the vehicle and the track itself.
Makes sense.
But maglev, which stands for magnetic levitation, eliminates physical contact entirely.
So it's floating.
Yeah, the vehicle floats above the track. It's propelled, guided, and lifted by incredibly powerful electromagnetic forces.
So the vehicle is literally flying. It's just flying a few inches off the ground.
That is the most accurate way to think about it, yeah. And because it is flying, the infrastructure requirements change at a molecular level.
How so?
Well, the core rules of maglev are brutal and non-negotiable. You cannot just take an underutilized freight rail corridor, rip out the wooden ties, lay down some magnets, and launch a maglev.
Oh, wow. Why not?
A true maglev system requires a dedicated, completely grade-separated guideway. It cannot ever cross paths with standard steel wheel tracks.
So no sharing the road, basically.
Zero. It cannot have a single intersection with an automobile road either. It operates inside its own exclusive, highly controlled physical envelope.
That's intense.
It is. And that single technological reality dictates every geographical and economic decision that follows in this framework.
So if traditional rail is like a winding river that meanders around a mountain and follows the natural topography of a valley and snakes through the center of a historic small town, maglev has to be treated more like a laser beam.
That's a great analogy.
The geometry of speed at 300 miles per hour is totally unforgiving, right? Can you explain that straight line requirement?
Yeah, the physics of moving a massive object at those velocities means curvature becomes your biggest enemy.
Okay.
If you try to force a maglev train to navigate a traditional rail curve, the centrifugal forces would just be intolerable for the passengers.
Like getting thrown against the window.
Exactly. And the structural shear stresses on the guideway would be catastrophic.
Yikes.
Consider Japan's Yamanashi test line, which is the proving ground for their superconducting L0 series maglev.
Okay.
The engineers designed that track with a minimum curve radius of 8,000 meters.
Wait, 8,000 meters? I am terrible at visualizing metric distances on that scale.
Yeah.
What does an 8,000-meter curve actually look like in the real world?
Think about drawing a circle on a map. For the Amanashi test line, the center of that circle would be almost 5 miles away from the edge where the track is.
Oh my gosh. 5 miles.
Yeah, it is a massive, sweeping, almost imperceptibly gradual curve. If you are a passenger looking out the window, you might not even realize the train is turning.
That is insane.
And they pair that incredibly wide radius with track grades, the steepness of the climbs and descents of up to maybe 4%.
Okay, so very gentle hills, very gentle turns.
Exactly. Now contrast that with the California High-Speed Rail project. They are designing for speeds around 220 miles per hour, but using traditional steel wheels on steel tracks.
Right.
Their design guidelines allow for a curve radius of roughly 22,000 feet, which is significantly tighter.
So it's much sharper.
Yeah. As your speed increases, the radius required to maintain passenger comfort and just, keep the coffee in the cup, it increases exponentially.
Well, wait, can't we just bank the track? You see that in NASCAR. The cars are going 200 miles an hour into a tight turn, and they stay on the track because the pavement is tilted at a crazy angle.
Right, right.
Why can't we just tilt the Maglev guideway to handle tighter turns around cities?
You can bank the guideway, and they do, up to a certain degree. It's called super elevation in civil engineering.
Okay.
But there is a fatal flaw with relying on extreme banking for passenger transit. A banked curve is only perfectly balanced for one specific speed.
Oh, I see.
If a NASCAR driver takes a heavily banked turn at 30 miles per hour, the car will literally slide down the incline toward the infield.
Gravity takes over.
Exactly. So if you bank a maglev track heavily for a 300-mile-per-hour curve, what happens if there is, say, a power fluctuation or a sequencing issue ahead and the train has to slow down to 100 miles per hour?
Oh, wow. The passengers would be thrown sideways against the interior walls.
The coffee goes everywhere.
So the forces become completely unbalanced if you aren't going the exact perfect speed.
Yes. You have to design the track so that if a train comes to a complete halt in the middle of a curve, the passengers aren't hanging upside down in their seatbelts.
That makes total sense.
Because of that limitation on banking, you are forced back to the original rule. The curves must be massive. This is why the Federal Railroad Administration essentially dictates that the ideal horizontal alignment for a maglev line is a perfectly straight line between 2 points.
A perfectly straight line.
The bones of this network must be drawn through straight, disciplined geometry.
Which completely breaks the instinct to thread this infrastructure through the existing layout of major cities, right?
Absolutely.
Or to try and weave it along the winding medians of old interstate highways through the mountains. You need vast, unobstructed open spaces to draw those laser straight lines.
You do.
But this leads to a very obvious question. If we possess this technology, this frictionless laser beam, why not just build a transcontinental ribbon right out of the gate?
Right. The LA to New York dream.
Exactly. If the objective is to revolutionize human travel, why not connect everything?
It sounds incredibly appealing, but it ignores the behavioral reality of how human beings consume transportation. It comes down to a concept the Federal Railroad Administration uses called the cost-benefit sweet spot.
The sweet spot.
Yeah. For high-speed ground transport, that sweet spot is strictly defined as the 150 to 500-mile range.
150 to 500 miles.
Corridors with high population density and strong city peer markets that fall within that specific distance are the only places where maglev economically thrives.
Let's test the boundaries of that sweet spot, though. Why does the system fail if the cities are closer together?
Well,
say we build a 50-mile maglev line between two neighboring cities. At 300 miles an hour, the train covers 50 miles in like 10 minutes. A 10-minute commute sounds like a utopian dream.
the math looks flawless there until you factor in the human being.
What do you mean?
The actual time spent levitating at top speed is only one fraction of the total door-to-door journey.
Oh, right.
You have to travel from your home or your office to the maglev terminal. You have to park your car or navigate local transit. You have to walk through a massive terminal complex, go through whatever security protocols exist, wait for the vehicle, and board.
That all takes time.
Exactly. Then, when you arrive in 10 minutes, you have to exit another massive station complex and secure local transit to your final destination in the new city.
So the overhead just eats the efficiency.
It dominates the trip. When the total distance is under 150 miles, station access and egress times completely ruin the speed advantage.
Wow.
If it takes you 40 minutes to navigate to the station and another 40 minutes to get from the destination station to your actual meeting, the fact that the train ride only took 10 minutes is statistically irrelevant.
Yeah, you could have just driven your personal car door to door in roughly the same amount of time.
With vastly more privacy, carrying whatever luggage you wanted, and without spending tens of billions of taxpayer dollars to build the guideway.
It's the same logic that tells you not to book a commercial flight to go 2 towns over. The TSA line alone makes it absurd. But let's look at the other extreme. If Maglev is so fast, why not use it for a 2,000-mile trip? Why does the sweet spot stop at 500 miles?
Because at those vast distances, aviation aggressively claws back the time advantage.
How so?
I have to look at the cruising speeds. A commercial airliner routinely cruises at 500 to 600 miles per hour.
Right.
A first-generation commercial maglev might cruise at 300 to 350 miles per hour.
Okay, so the plane is just fundamentally faster in the air.
Exactly. For a 300-mile trip, the maglev wins the race effortlessly because the airplane speed advantage is completely negated by the sheer friction of the airport experience.
Right, the security theater, the boarding zones, the taxiing, the holding patterns.
Yes. But if you are traveling 2,000 miles, that extra 200 miles per hour of cruising speed that the jet possesses begins to compound.
Oh, I see.
Over the course of 4 or 5 hours, the airplane's raw velocity overwhelms the inconvenience of the airport.
So if you think about the last time you went to the airport, you weigh the indignity of taking off your shoes, unpacking your laptop, standing in boarding group C.
We all hate it.
Right. You weigh that against the prospect of walking onto a perfectly timed, spacious, silent train that drops you off 300 miles away in under an hour.
The train wins every time.
For a trip from Washington, D.C. to New York or Dallas to Houston, the Maglev feels like a miracle.
But if you are trying to get from New York to Seattle, you are going to get on a plane. The math is inescapable.
So this means the national build strategy cannot be a single, heroic, symbolic, transcontinental ribbon.
It absolutely cannot. A continental system must be assembled as an overlapping chain of 150 to 500-mile markets.
Okay.
It has to emerge organically as a lattice of highly profitable, highly utilized regional segments. You string the pearls together one by one. You do not try to cast a single net across the entire ocean.
So if we know we need straight lines, and we know we need them in 150 to 500-mile chunks, how do we decide which cities to connect first?
That's the big question.
What is the master blueprint? And this is where the planning framework takes a really wild turn.
It really does.
Because the ultimate architectural guide for a trillion-dollar American infrastructure project comes from a brainless, single-celled organism.
Saphizarum polycephalum.
Yes.
The slime mold. It sounds absurd to bring a gelatinous blog into a discussion about electromagnetic transit policy, I know.
It's totally nuts.
But the biological lessons it provides are profound and mathematically rigorous.
I was reading about this 2010 study from the journal Science that the framework relies on.
Mm-hmm.
The researchers did something brilliant.
Yeah, it's a famous experiment now.
They took a physical map of the Tokyo area and placed ode flakes, which the slime mold uses as a food source, at the exact geographical locations of Tokyo and the surrounding major cities like Yokohama and Chiba.
Right.
Then they released the slime mold in the center, right on Tokyo.
And the initial behavior of the organism is exploratory. It spreads out in a dense, chaotic, highly redundant spider web, blindly searching its environment for resources.
Just a giant, messy blob.
Exactly. But once it locates the oat flakes, the behavior completely shifts.
What does it do?
It does not maintain that messy spider web. It begins an incredible process of self-optimization. It retracts the protoplasmic tubes that are inefficient.
Wow.
It stops sending energy down dead ends. Instead, it reinforces and thickens the most direct, high-capacity connections between the food sources.
And when the researchers laid the slime mold's final optimized network over a map of the actual Tokyo rail system, they were nearly identical.
It is a stunning visual. A brainless amoeba recreated the work of Japan's most elite civil engineers.
That is just mind-blowing.
What's fascinating here is that the slime mold is not attempting to draw a map that looks aesthetically pleasing to a politician.
Right. It doesn't care about optics.
It is actively solving a complex optimization problem. It is forming a network that strikes a ruthless balance between 3 competing priorities: cost, transport efficiency, and fault tolerance.
Okay, let's break those down.
In biological terms, cost is the raw caloric energy required to maintain the physical structure of the protoplasmic tubes.
Make sense?
Efficiency is the speed at which nutrients can flow through those tubes from one node to another.
Okay.
And fault tolerance is the organism's insurance policy. It ensures that if a predator severs one tube or the environment degrades, the whole organism doesn't instantly starve to death.
So how do we translate the caloric math of a hungry yellow blob into federal transportation policy?
We adopt its ruthless pragmatism. You do not ask the Department of Transportation for a pretty national spider web that gives every single state a Maglev station just to satisfy political
You
fairness.
can't just hand them out like candy.
Exactly. You let the topology reveal the smallest number of massive high-capacity trunks that carry the most value.
The thickest tubes.
Right. And then crucially, you only construct the minimal number of secondary fallback loops necessary to ensure network resilience. You design a thick, powerful skeleton. You do not build a delicate, brittle web.
This biological logic forces a massive narrative shift.
It really does.
If we are strictly looking for the ability to draw incredibly straight lines over relatively flat terrain, to connect major population centers that sit exactly in that 150 to 500-mile sweet spot, we are suddenly forced to look away from the congested, hyper-expensive, mountainous, and densely packed coasts.
Yes.
We have to stare directly at the American Midwest.
This is the most controversial, yet structurally unassailable argument in the entire framework. The epicenter of American high-speed transit cannot be New York. It cannot be Los Angeles.
So where is it?
It must be Nebraska.
Okay, I have to push back on this because from an economic standpoint, it sounds ridiculous.
I know it is.
A trillion-dollar transit system needs riders to pay the electric bills. If you start this futuristic project in Nebraska, the fare box recovery is going to be non-existent compared to the Northeast Corridor.
That's the traditional argument, yes.
Right. It sounds like a political gimmick to win votes in flyover country, not a serious economic strategy. How do you justify starving a new transit technology of coastal riders?
You justify it by looking at the raw physical and operational requirements of the technology rather than the traditional transit mindset.
Okay.
The framework acknowledges that Nebraska lacks the population density of the eastern seaboard. But Nebraska offers something the eastern seaboard literally cannot provide at any price: unimpeded geometry and available industrial scale.
Unimpeded geometry.
Yes. The strategy hinges on a specific concept: the dual center architecture. You do not just drop a pin on Omaha and hope 1 million people show up to ride the train.
What does dual center architecture actually look like in practice?
It means the network requires 2 distinct hubs serving 2 completely different biological functions. You have the passenger gateway and you have the machine room.
Let's examine the passenger gateway first.
Recent census data shows Omaha has a population pushing 500,000, and nearby Lincoln has over 300,000.
Okay, so that's decent.
Combined, that is a robust, legitimate metropolitan footprint. Omaha becomes the front door. This is where you locate the soaring glass terminal.
The shiny part.
Exactly. This is where you build the seamless intermodal transfers connecting the Maglev to the local bus networks and the airport. It becomes the public face of the system. It provides the political legitimacy, the visible ridership base, and the corporate headquarters.
So if I am a business traveler, I'm buying a ticket out of the Omaha terminal. To me, the rider, Omaha is the center of the universe.
Right.
But the actual center of the universe, the metabolism keeping the entire system levitating, is somewhere else entirely.
It is in North Platte, Nebraska, specifically Union Pacific's Bailey Yard.
I was looking at the satellite imagery of Bailey Yard. The scale is difficult to comprehend.
It is the largest railroad classification yard on the planet.
Wow.
We are talking about over 2,800 acres of pure, unadulterated industrial rail infrastructure.
That's massive.
It sits perfectly at the intersection of critical east-west and north-south transportation corridors.
But North Platte is small, right?
Very small. The population of North Platte itself is tiny, around 22,000 people. You would never build a gleaming passenger terminal there based on ticket demand.
Right. But Maglev is not just a mechanism for moving people. It is a massive, incredibly heavy system of systems.
Let's drill down into what that system of systems actually entails. If we are running a nationwide fleet of levitating vehicles at 300 miles an hour, what is happening backstage? What does a Maglev pit crew look like?
The back-end logistics are industrial in scale. First, you need facilities for heavy maintenance. These vehicles undergo immense aerodynamic stress.
Sure.
Second, you need precision guideway fabrication. You aren't just laying wooden ties and steel rails. You are casting massive, reinforced concrete guideway segments to millimeter tolerances.
So you need a factory, basically.
Exactly. You need a colossal staging area to mix, cast, cure, and ship those components out to the construction fronts.
I saw a mention of turnout-free trunk dispatching. What does that mean? Is a floating train not switch tracks like a normal train?
A traditional train switches tracks using a small set of moving steel points. It takes seconds.
A maglev vehicle wraps its undercarriage around the massive concrete guideway. To switch tracks, you have to physically bend or articulate enormous, multi-ton sections of the guideway itself while maintaining microscopic alignment tolerances.
Oh my goodness. That sounds complicated.
It requires massive mechanical infrastructure and vast amounts of physical space to build a high-speed switching yard. Furthermore, you need traction power management.
Power management.
Unlike a diesel train that carries its fuel, a maglev vehicle is propelled by the track itself. The guideway is essentially a continuous, linear, synchronous motor.
Okay.
You are pulsing megawatts of electricity into the track, perfectly synchronized with the speed and location of the train. The substations and grid connections required to manage that power are immense.
And you need a place to physically park the vehicles, too.
Exactly. You need vast acreage to park, inspect, clean, and rotate the spare vehicles overnight so you can deploy them efficiently for the morning rush across the network.
So what does this all mean? It means you cannot build a 2,800-acre concrete fabrication and power management yard in downtown Manhattan.
Never.
You couldn't even build it in the far suburbs of Chicago or Los Angeles. The land acquisition costs, the eminent domain battles, and the environmental impact studies would bankrupt the project before you poured a single ounce of concrete.
North Platte is practically tailor-made for the industrial half of the maglev equation.
Right.
It is culturally, geographically, and operational organized around rail scale. The community understands heavy infrastructure.
They're used to it.
It has the open land, the existing logistical pathways via legacy freight to bring in raw materials, and the industrial mindset.
Yeah.
The dual center logic creates an incredibly healthy division of labor.
It's a separation of church and state.
Yeah.
The public cuts the ribbon in Omaha.
Hmm.
The politicians shake hands in front of the cameras. But the system survives day in and day out because of the invisible industrial muscle flexing in North Platte. It is the heart and the lungs of the network, operating out of sight, free from the constraints of urban real estate.
And acknowledging that separation is vastly healthier than pretending every new national system needs its first sacred all-in-one center planted in the middle of our most expensive, constrained coastal cities.
So we have our heart and our lungs functioning in Nebraska. How does this biological organism grow its skeleton?
Right, let's map it out.
If we look back at the slime mold and we combine its logic with the existing gravitational pull of federal high-speed rail planning, what does this first-wave prairie skeleton look like geographically?
The framework models 4 primary corridors originating from this Nebraska core. The first is the Eastern Trunk, Omaha to Chicago.
Okay, Omaha to Chicago.
This spans roughly 500 miles, placing it perfectly on the outer boundary of our cost-benefit sweet spot.
The 500-mile limit.
Yes. Crucially, there is real political and historical gravity here. The federal government has already studied and allocated resources toward understanding the Chicago to Omaha corridor. Chicago is the vital eastern hinge.
Chicago is the gateway. If you build a train in Nebraska and it doesn't connect to Chicago, you haven't built a national network. You've built an expensive regional novelty.
The framework refers to it as an indispensable eastbound tendon.
I love that.
An inland trunk stops being a regional experiment and becomes a true candidate for national expansion the exact moment it integrates with Chicago Union Station.
It connects to everything else.
It unlocks the entire Great Lakes region, sets the stage for the eventual push to the East Coast.
Okay, so that's the Eastern Trunk.
The second corridor is the Western Trunk, Lincoln and North Platte reaching out to Denver.
Denver's an interesting choice. It's not a coast. It's not even close to a coast. If the goal is to eventually reach Los Angeles, why stop in Denver? Why is Denver the priority going west?
Because of the topography.
Yeah.
A Nebraska to Front Range segment is one of the cleanest, most efficient inland maglev corridors possible.
Oh, because it's so flat.
It allows engineers to exploit incredibly long, straight reaches across the Great Plains. The grades climbing toward Denver are moderate, essentially a long, gradual ramp compared to true mountain railroading.
Sure.
Denver acts as a natural demand bridge between the plains and the Rockies. In strategic network terms, Denver behaves like a westward staging ground.
But a staging ground.
You establish a massive, undeniable western anchor on the edge of the mountains, consolidating your operational strength and proving your ridership models before you even attempt to tackle the vastly more difficult, hyper-expensive engineering nightmare of tunneling through the Rockies to reach the Pacific.
It's base camp before you climb Everest.
Exactly.
Okay, we have our east-west line established. Omaha to Chicago, Omaha to Denver. What about the third corridor?
The third is the southern hinge. Omaha down to Kansas City, and then Kansas City crossing over to St. Louis.
Okay.
This is where the biological lesson of the slime mold truly proves its worth in civil engineering.
How so?
If you only build a single horizontal spine, say, a straight shot from Omaha to Chicago, you have created what engineers call a brittle star.
A brittle star.
Every piece of inland movement relies entirely on that one single tendon.
Oh, I see. So if a massive blizzard dumps 3 feet of snow across Iowa, or there's a catastrophic power substation failure near Des Moines, the entire national network is severed in half. There's a single point of failure.
The Kansas City to St. Louis lower loop provides the required fault tolerance.
Ah, the insurance policy.
It gives the interior network a second path to Chicago. It gives it a second path heading south toward the Texas Triangle and a second path heading east toward the Ohio Valley.
That's brilliant.
Kansas City ceases to be just another dot on a map. It becomes the vital hinge that prevents the entire architecture from becoming a one-spine, one-failure system.
It's the secondary protoplasmic tube. The slime mold refused to prune because it knew it needed insurance.
Oh, I see.
And the fourth corridor.
The northern branch. Chicago pushing up to the Twin Cities, Minneapolis, and St. Paul. Notably, the framework dictates that the Omaha core accesses the Twin Cities through Chicago, rather than trying to force an awkward diagonal line straight from Nebraska up to Minnesota as a first move.
Wait, a diagonal line from Omaha to Minneapolis looks shorter on a map. Why not just draw the straight line?
Because you have to respect the existing gravity of infrastructure planning.
Okay.
The federal government, along with multiple state DOTs, has already poured immense political capital and planning resources into the Chicago, Milwaukee, Madison Twin Cities corridor.
So the groundwork is already laid.
The gravitational pull of population density and political will is already established there. A rational, pragmatic Maglev program doesn't fight that existing gravity, it absorbs it.
Makes total sense.
So your first interior grid becomes beautifully legible. Nebraska out to Denver westward, Nebraska to Chicago eastward, Nebraska dropping to Kansas City southward, forming a resilience loop through St. Louis back up to Chicago, and Chicago branching north to the Twin Cities.
That is a living, breathing inland skeleton. It has massive trunks, it has resilience loops, and it completely bypasses the catastrophic instinct to start the project by digging a $10 billion tunnel under the Hudson River.
Exactly.
But how we actually physically build this skeleton introduces a build doctrine that is going to shock anyone used to the way America traditionally builds transit.
It definitely will.
We have to stop thinking of Maglev as an upgraded Amtrak train. The analogy used is that we must start thinking of Maglev as aviation corridors pinned to the ground.
That is the only mental model that accurately reflects the reality of the technology, because Maglev requires a completely dedicated, grade-separated guideway. You cannot treat it like legacy rail.
Right.
The doctrine dictates that you cannot blindly shadow a legacy freight rail corridor just because the right-of-way already exists.
Why not?
Freight lines curve, they meander around property lines, they adapt to the subtle terrain. A 300-mile-per-hour maglev cannot weave.
Right, the 8,000-meter radius rule.
Exactly. Instead, it must follow perfectly straight utility corridors, massive interstate medians, or broad, open transportation reservations that allow for uncompromised geometry.
This brings us to the most brutal part of the doctrine: how the system interacts with cities.
Yeah, this is a tough one.
The traditional, deeply ingrained transit mindset in America is that a train is fundamentally useless unless it drops you off right at the front steps of City Hall.
Right.
But the framework rejects this entirely. It explicitly states that the guideway should not be dragged through every single downtown.
It is a bitter pill for transit advocates, but the physics and the economics absolutely demand it.
Okay.
The framework proposes a strict, unforgiving station hierarchy. At the apex, you have metropolitan terminals.
Metropolitan terminals.
These are the massive downtown integrated architectural marvels, but they are only built where the immense cost of deep-bore tunneling into an urban core is justified by an overwhelming guaranteed return in ridership and surrounding land use.
So, Chicago certainly merits a metropolitan terminal. Omaha, Serving as the system's flagship front door might merit one.
Yes.
But smaller cities do not automatically get one just because the train passes nearby.
The next tier down is the through running edge station.
Okay.
This is utilized where forcing the maglev to detour from its straight path to reach a dense downtown would ruin the geometry of the national trunk and add billions of dollars in tunneling costs.
So what do they do instead?
In these instances, the maglev stops at the periphery of the city, perhaps near an existing interstate ring road or a regional airport. Local transit light rail, subways, express buses, or ride shares handles the last mile distribution into the downtown core.
Got it.
The framework states it plainly. Downtown access must be earned economically. It is not a religious obligation at every single stop.
Downtown access must be earned. That is such a cold, rational way to look at it.
It is.
If the mayor wants the train in the city center, the local market has to prove it's worth the $5 billion tunnel. Otherwise, the city gets a sleek edge station by the highway and the passengers take an Uber.
And the third tier of the hierarchy encompasses the logistics nodes.
Like North Platte.
Yes, these are places like North Platte. They are systems campuses first, focusing on maintenance, power, and fabrication, and passenger stations second if they bother to serve passengers at all.
Along with this rigid hierarchy, the framework has an absolute mandate regarding the tracks themselves. It insists on dual tracks everywhere, without exception.
Yes, this is critical.
Why is this a hill to die on? If the entire point of starting in the Midwest is to manage costs, why not build a single track across the plains?
Yeah.
We could have trains take turns going in opposite directions, passing each other at strategically placed stations. American Regional Rail does this constantly to save money.
And that single-track methodology is precisely why American Regional Rail is frequently plagued by cascading delays and severe capacity limits. The framework refers to single-track compromises as capacity traps. In the open country of the American Midwest, land is relatively cheap and construction is relatively straightforward.
Right.
This is exactly the environment where you must spend the capital on straightness, robust grade separation, wind hardening against severe weather, and most importantly, dual guideways.
So don't keep out where it's easiest to build.
Exactly. If you choke the capacity of your national trunk in the middle of a Nebraska cornfield just to save a few dollars up front on concrete, you permanently ruin the utility of the entire multi-trillion-dollar network.
You create a bottleneck that ripples across the continent.
The fixed costs of acquiring the right-of-way, conducting the environmental studies, and building the immense electrical substations remain incredibly high even if you only lay one track.
So it's not actually half the cost.
You do not save 50% of your budget by building one track instead of two. You might save 20%, but you strangle your operational capacity by more than half. Passing loops might work for a freight train going 40 miles an hour. They do not work for vehicles approaching each other at a combined closing speed of 600 miles an hour.
Yeah, that sounds like a recipe for disaster.
You economize by choosing cheaper, open geographical corridors, not by starving the central trunk of its physical capacity.
Okay, the cost. That is the elephant in the room. That is the monster lurking behind all of this beautiful biological theory and geometric planning. This is where the dream either becomes disciplined or it completely unravels. Let's talk about the actual price tag.
The cost architecture is the harshest reality check in the entire document.
It is sobering.
The sources provide a historical baseline to show how far our assumptions have drifted. An old FRA report utilizing 2004 dollars estimated that maglev projects would average roughly $40 million to $100 million per mile, with heavy urbanized systems hitting the higher end.
Right.
But as the framework points out, relying on 2004 figures is basically relying on ancient mythology. We have to look at modern, hard realities to understand the financial precipice we are standing on.
The modern reality is genuinely terrifying. The framework highlights what it calls the nightmare baseline.
Yes.
The Baltimore-Washington SCMVG-LEV project. SCMG-AV stands for Superconducting Maglev, the Japanese technology.
Right.
This is a proposed line connecting Baltimore to Washington, D.C., two major vital cities on the East Coast. It is a tiny route. It is only 33 to 35 miles long.
Very short.
But because it is situated in one of the most densely populated, politically complex, and geographically constrained corridors in America, the design requires 75 to 83% of the route to be built in deep subterranean tunnels.
And when you tunnel for Maglev, you aren't just digging a normal hole.
Why not?
Because of the incredible air pressure generated by a vehicle displacing air in an enclosed tube at 300 miles per hour, it's called the piston effect. The tunnels have to be massive.
Oh, right. It's pushing all that airflow.
Yes. You need complex ventilation shafts punching up to the surface every few miles, which means acquiring impossibly expensive real estate in downtown D.C. and Baltimore just to build an air vent.
That is nuts. The estimated cost for those 35 miles is nearly $20 billion.
Unbelievable.
$20 billion to shave maybe 15 minutes off a commute that the existing Amtrak Acela already serves.
It is a catastrophic figure that destroys the cost-benefit ratio. And to prove that this isn't exclusively a symptom of American infrastructure dysfunction, the framework points directly to the Japanese benchmark.
Okay.
JR Central is currently constructing the Tro Shinkansen, a superconducting maglev route from Shinagawa in Tokyo to Nagoya.
Right.
It is heavily tunneled through mountainous terrain. In October 2025, they forecast the cost at 11.0 trillion yen.
Which is how much?
Using the exchange rate cited in the paper for March 2026, that translates to roughly $68.9 billion.
So whether you are dealing with the zoning boards in Maryland or the geological realities of tunneling through the Japanese Alps, if you try to force a maglev through a dense, complex environment, the costs become astronomical.
Which leads to the inescapable foundational conclusion of the entire framework. Inland, open country surface maglev, like our Nebraska to Denver trunk, and tunnel-heavy metropolitan maglev, like Baltimore to Washington, are two entirely different economic species.
They aren't even the same game.
You cannot price them the same way, you cannot plan them the same way, and you absolutely must not sequence them the same way.
So the framework actually models the math for the phased build-out of our inland skeleton. How do the numbers scale when we stay in the open country?
Phase IA is that core prairie skeleton we mapped out. Omaha to Denver, eastward to Chicago, southward to St. Louis, and north to the Twin Cities.
Yeah.
That comprises roughly 2,210 route miles. The author models a middle case cost assumption of about $260 million per mile.
Right.
When you add a 15% layer to account for the massive systems integration, the terminals, and the power grid connections, the total for Phase IA comes to roughly $660.8 billion.
Over $500 billion. And that is just to build the Midwestern core. What happens when the slalom mold expands its network?
Phase IB extends that skeleton south to create what is called the Texas Arc. It drops from Kansas City down to the Dallas-Fort Worth Metroplex, pushes over to Houston, and cuts across to San Antonio.
Oh, that's a huge addition.
It is. This expansion brings the total network to roughly 3,150 miles. Using the same baseline assumptions, the cost swells to roughly $941.85 billion.
Getting close to $1 trillion.
And if they encounter a tougher cost scenario regarding land acquisition or material inflation, Phase IB easily exceeds $1.2 trillion.
And if we extrapolate that logic all the way out to a true, mature national grid, say, a 9,500 to 11,000 mile network that finally fulfills the dream of reaching the coasts, the numbers become almost incomprehensible.
So they do.
The model shows it stretching from $2.85 trillion to nearly $5 trillion.
Those staggering figures are precisely why the framework insists that a real U.S. Maglev program is a multi-trillion-dollar undertaking, not a few hundred billion pet project that can be squeezed into a standard highway bill.
Yes.
And if we connect this to the bigger picture, it is the exact reason why the traditional coastal strategy is doomed to fail. We have to look at the grim political lesson of the coast.
What happened?
The framework highlights a critical historical event. In August 2025, the U.S. Department of Transportation outright canceled over $26 million in federal grants that were destined for that Baltimore-Washington SCMALE-LV project.
Wow. They pulled the plug because the $20 billion cost was untenable, the delays were compounding, the local opposition from neighborhoods sitting above the proposed tunnel routes was fierce, and the environmental litigation was endless. It became a political quagmire.
That cancellation is the ultimate lesson in infrastructure delivery.
How so?
The West Coast California specifically is incredibly dense, environmentally sensitive, and geographically walled off by mountains and oceans.
Very tough to build in.
The East Coast is essentially one unbroken chain of hyper-dense urbanization stretching from Boston down to Washington.
Right.
These are the two most difficult, expensive, and legally treacherous national ladders to climb.
So starting there is a mistake.
If you open your national Maglev campaign by attempting to build in the hardest, most expensive urban corridors on Earth, you mathematically maximize your chance of failure.
That makes total sense.
The public will watch billions of dollars burn in endless environmental review litigation, land use battles, and tunneling nightmares. They will learn to associate the very word maglev with trauma, political corruption, and systemic failure.
You poison the well before you even draw a drop of water. If the first headline the public reads is about a $5 billion cost overrun on a tunnel in Maryland, they will never authorize the funding to build the rest of the network.
The framework's doctrine dictates that the East and West Coast ladders must be built last.
Last.
You build the inland network first, you build out in the open prairie where the physical geometry is favorable, the land acquisition is cheaper, and the construction pace is incredibly fast.
You get some quick wins.
Exactly. You create an operational system that is visibly fast, visibly useful, and visibly achievable without a decade of tunneling delays. You generate a massive inland economic engine that proves the fundamental technology actually works.
Yeah.
By achieving those visible wins, you earn what the framework brilliantly calls a social permission structure.
A social permission structure. I love that term. You prove to the American taxpayer that Maglev is real, that it's transformative, and that the government is actually capable of building it.
Yes.
And then, only after you have established that trust, do you ask them to stomach the multi-billion-dollar tunneling costs required to finally link New York and Los Angeles to the national grid.
You earn the political capital to tackle the hard stuff. It is a brilliant subversion of how we usually think about prestige infrastructure.
We always want to start with the crown jewels.
Yeah.
We want the ribbon cutting in Times Square.
Right.
But this framework is telling us that to build a lasting empire, you have to start by laying the plumbing in the basement. The inland lattice is not a detour from the national vision. It is the only credible road into it.
To bring this all together for you, the source material leaves us with a final thesis that beautifully summarizes this entire radical approach.
Right.
A national U.S. maglev system should not begin as a beautiful coast-to-coast monument. It needs to be engineered according to 3 immutable laws.
Law number 1, topology.
Yeah.
We follow the logic of the slime mold. We build a few massive high-capacity trunks first, and we only add secondary loops, where they materially improve the fault tolerance and resilience of the network.
Law number 2, geometry. We bow to the reality of maglev physics. Straightness is the governing variable. We use dedicated guideways, we demand massive curve radii, and we ruthlessly ration our urban penetrations, meaning downtown access is an economic privilege, not a right.
And law number 3, phasing. We respect corridor economics. We build those overlapping 150 to 500-mile markets in the open interior of the country first. We establish the machine room in Nebraska. We save the symbolic hyper-expensive coasts for the final chapters.
Embracing this requires a profound shift in our cultural mindset regarding infrastructure. True progress on a multi-trillion-dollar scale requires letting go of the glamorous poster.
Right.
We have to surrender the romantic map of a coast-to-coast ribbon in favor of an unglamorous, geographically pragmatic operational truth. We have to be willing to start in Nebraska.
Honestly, it is a lesson that extends far beyond just building trains. It is about how we approach any massive, complex system in our modern world. Which brings us to a final thought for you to mull over as you go about your day.
If starting with the hardest, most symbolic coastal cities is the exact wrong way to build a continental maglev network, what other massive national challenges like upgrading our failing electrical grid or planning our next-generation space infrastructure are we currently failing at, simply because our map-making ego is getting in the way of our slime mold pragmatism?
It makes you wonder how many beautiful presentations are actually just blueprints for disaster. Thank you for joining us on this deep dive. Keep asking questions, keep looking beneath the surface of the next big infrastructure headline, and we will catch you next time.